Hello everybody, my name is KETAN and we will discuss my work on building a custom domain specific accelerator for real-time CNN inference. First, why do we require custom processors? Well, the reason is that because we are witnessing the end of Dennard scaling's law. So Dennard scaling was a phenomenon wherein reducing the transistor size reduced the voltage and the capacitance but kept power density constant. This means that because the transistors are smaller size, we can pack more transistors per unit area and the power density will be constant. So we get more performance at the same power demand. We could also increase the frequency of the processors. That's why the speed of the processors increased from megahertz to gigahertz. However, post 2005, we have seen that reducing the transistor size no longer reduces the power consumption per transistor because leakage current becomes dominant. This means that clock frequencies are becoming saturated at around 3 to 4 gigahertz. And instead of trying to increase the clock frequency, all the powerful computers are adding more cores. So now we have more cores in each computer, 8 cores, 16 cores, and hundreds of cores. So this is the fundamental limitation. Once we reduce the transistor beyond a particular size, there is too much leakage current and the power density does not reduce even if you reduce the transistor size. This means if you try to add more transistors or if you try to increase the frequency of the clock, the power consumption will increase linearly. This is especially very problematic if you are trying to create chips for smartphones and laptops because they have a very limited power budget. So one of the ways to counter this is something called the dark silicon, in which case we are adding more transistors to our chip, but at a time we are not using all the transistors. So that means a fraction of the chip is not being used at all, no power is being supplied to it. These chips are usually specialized accelerators, which means they are not always used, they are only switched on when a specific task has to be performed. So if you have a particular chip of some particular size A, some percentage of that chip will be switched off until it is needed, whereas the general purpose chip will always keep on running. So this way we are able to increase the functionality and performance, but we also have to take care of switching on and switching off the number of transistors. So this is called heterogeneous computing, which means we have on the same chip, we have multiple different functionalities. One will be a general purpose CPU, one will be a video processing unit, one can be a AI processing unit, etc., etc. So this is why we are moving towards heterogeneous computing. Nowadays, every CPU core that we have is already heterogeneous. So it has multiple, it has a neural engine, it has a GPU inbuilt inside it, it has video encoding, decoding, it has some DSPs, etc., etc. So now we are moving away from simple microprocessors into a heterogeneous system which does different functionalities, but they all reside on the same chip. Now let us talk about edge computing. Why is edge computing so hard? One of the reasons why edge computing is so hard is that we need to compute on very cost-effective processors and cost-effective hardware. We cannot buy extremely powerful and expensive hardware. The second is area limitation. We cannot put a big chip inside our CCTV cameras or inside small sensors. We have a very limited area, and we also have very limited power. So we cannot have powerful cooling systems or big fans. So we have very limited power, maybe a small battery, and the entire workload must run on that. So this is why edge computing is so hard. But the benefit of edge computing is that it's faster. You don't need to send your data to a cloud. And also there is a lot of privacy because everything is done locally. Some of the examples of edge computing are real-time object detections in drone. Then you have wake word detection, like when you say, "Hey Alexa" or "Hey Siri." Then text-to-speech and also vision detection in factories. So all of this must happen on a small board because the power and area are limited. Now, why do we need to build a custom accelerator? Why can't we use a small CPU? Well, one of the reasons is that CPUs spend most of their time performing overhead operations rather than actual arithmetic operations. So if you from literature survey, we can see that about 5 picojoules of overhead is there per 0.2 picojoules of real arithmetic. So where is the overhead coming from? So it's coming from fetching instruction, then we have to decode the instruction, then we have to read the registers, then finally we do the arithmetic instruction, and then we also have to write back the data. So the executing the instruction is not actually taking a lot of energy, but performing all the other necessary operations are taking a lot of energy. So this is a little bit inefficient in many cases. So how can an accelerator help us? So the accelerator can remove the fetch, decode, and issue pipeline. So the accelerator is not general purpose like a CPU. It does not fetch instructions, it does not decode instructions. All the operations are actually hard coded into the accelerator. So the accelerator can only perform a certain set of instructions, certain set of operations, sorry, which are hard coded into the silicon itself. So it is not a general purpose fetch, decode, issue pipeline. So you can expect around 10 to 1000 times better performance per watt, but what you will lose out is generality. So you cannot perform arbitrary algorithms on an accelerator, whereas in a CPU you can perform many types of algorithms, addition, multiplication, graphs. But on an accelerator you have to limit your application to maybe one or two use cases only. In return for that, you will get much better performance per watt. So now here is the accelerator that I designed using System Verilog. So I wrote the complete RTL code in System Verilog end to end. My accelerator follows a control status register interface, which means my accelerator has certain special registers which are telling the accelerator what operation to perform and what are the parameters for these operations. So these are similar to the special registers that we see on microprocessors, like the program counter, stack pointer. So my accelerator also has some special registers. Then there is a on-chip memory. So my accelerator has all the a lot of memory. So the key goal is to keep most of the memory on the accelerator itself instead of putting it on the RAM, which will again take more latency from going to the RAM, going to the memory which is far away and fetching it. That will take more time. So most of the memory is kept on chip. Then there is the host accelerator software stack, which means to control the accelerator, we also must have a host system, which is the ARM CPU. So the ARM CPU will only perform basic control operations, and most of the computation and performance will be done on the accelerator itself. So this is called the host accelerator split. So the host will perform all the necessary control and organizing of data, but actual instructions will be executed rapidly by the accelerator. All the multiplications and additions that we need to do, all the matrix multiplications basically that we need to do. So if you we will look at our workload. What is our workload? Since we are running a CNN, which is for vision detection, we have billions of multiply accumulate operations per second. So you have in matrix multiplication, the basic arithmetic operation is multiplication addition, ax plus b. So we have billions of such operations. So this is the key. We know that most of our operations are going to be multiplication and addition. This is why we can limit our accelerator to focus only on these two operations, and we don't have to a lot of operations which are there in the processor CPU are going to be not useful for running a CNN, which is why CPUs are not very useful and efficient for running a CNN. So this is the board that we are using. It's called a heterogeneous system on chip. Why is it heterogeneous? Because it has an ARM processor, which is 4 cores. It also has a GPU, and it has a programmable logic, also known as FPGA. So FPGA is where we are going to build our custom accelerator, and the arithmetic processing and the CPU ARM processor unit is what is going to control our FPGA. We will not be using the GPU and the RPU. How is the accelerator and CPU partition? This is very important because a CPU has its own advantages and accelerator has its own advantages. So CPU is good for controlling and sequencing. So it is good for organizing and controlling the accelerator, and it is good for code wherever there is control flow, like if there is loops or if there is if and else statements, then the CPU is really good. The accelerator is good for performing dense convolution. Again, convolution is the most important layer in CNN. It does a lot of kernel sliding, multiply, accumulate operations. So this is where the accelerator will be useful, because we have a very homogeneous operation being performed, multiplication and addition repeatedly. We are not having any loops or any conditional statements, we are or any branches, etc. We are just having a set of multiplications and additions performed. So this is where the accelerator will shine, and it will compute all of this in parallel instead of doing one by one sequentially like a CPU does. It loads one instruction, executes it, then loads the next instruction, executes it. So this sequential thing can be avoided in our accelerator. So in short, CPU will handle the irregular and controlling of the accelerator. The accelerator will handle the computationally heavy parts of the process. This is the top level architecture. So you can see that we have our ARM processor here. The weights of the model will be loaded, the image pixels will be loaded, and a memory will be allocated for storing the output result also, like the classification of the object detection. AXI Lite is a protocol that is used to communicate between a CPU and any other device. So we are in our case, our device is the programmable logic, which is FPGA board. So we will communicate between the CPU and the FPGA board using the protocol called AXI. AXI comes in many different variants. AXI Lite is one protocol, AXI Master is one protocol, and AXI Streaming is the third variant of AXI protocol. So we will be using AXI Lite and AXI Master. So AXI Lite will be used to control the FSM, so control the FPGA. So like the few special registers, the ARM CPU can control those special registers using AXI Lite protocol. The reason is that those registers are really small, only 64 bits. So we don't need a very heavy and bulky protocol for communication. So we will use the AXI Lite protocol. AXI Master protocol will be used to load the weights into the FPGA. So the FPGA will directly go to the RAM only once, only in the initial setup stage. It will go to the RAM and it will read the weights. It will read the input image, pixels of whatever input image it has to detect, and it will do that using AXI Master protocol. Then it will go through the CNN operations, which are kernel window, then convolution, then quantizer, and then the final layer is max pool layer. It will perform those layers, and then it will finally, again using AXI M protocol, write the output into the output buffer. Another thing to note is that our FPGA is running at 250 megahertz. So this is the clock speed of our FPGA. The clock speed is much slower compared to what CPUs run at. CPUs run at usually gigahertz order. But since CPUs spend most of the time decoding instructions, fetching from memory, issuing instructions, etc., that the clock speed benefit is not being fully utilized. So even though we are using a much lower clock speed, we will still be able to get much better performance for our CNN network. So this is about the AXI protocol, which I spoke about briefly. It is basically to communicate between the CPU and the FPGA. These are our special registers which I was talking about. So there is the control register which indicates the FPGA to start. If it checks when the FPGA is done, it checks if the FPGA is not doing any operations right now. Then we have to configure where to store the weights, where to store the biases, where is the pixels of the image, and where to store the output of the accelerator or the FPGA. So these are some certain parameters which are controlled by the CPU. So the CPU will set these registers using the AXI protocol. So this is our accelerator FSM. FSM is finite state machine, and this is what the accelerator. These are the different internal states of the accelerator. So like the CPU has instruction fetch, instruction decode, instruction, all these different states, all these different operations. Our FPGA also has different operations, which is first is the loading stage, which will then is the loading the weight stage, and then is the performing the actual operations, then is finally writing the output. So this is just a representation of what our FPGA is doing internally. So now this is where our advantage is coming from. In every cycle, we are doing these 7 operations in parallel, not sequentially. So we are fetching the pixel, the input image pixel. We are multiplying it in parallel with many output features and input channels. Then we are adding those results, and then we are storing it back. So all of this is being done in parallel. So how are we doing it in parallel? Our accelerator has something called a convolutional processing element. So you can consider it as one core. So like CPUs have multiple cores, even our accelerator has 8 cores, 8 parallel cores. So each of those cores performs the convolution operation in parallel. So total 8 convolution operations we can do in parallel. Per PE, we are using 72 DSPs. What are DSPs? So DSPs are a certain specialized blocks on the FPGA which are very efficient and fast for multiplication and addition operations. So we are trying to maximize the usage of DSP blocks, so that we can perform our multiplication and addition extremely fast. We have two sets of parallelism. Again, I will not go into too much details here, but we are also, so each image has certain number of input channels. As we all know, RGB is 3 input channels, but later on in CNN we can have more input channels, and also each image, each layer has an output channel, also number of channels. So all this is decided by the CNN architecture and the CNN model, which model we are using. That will specify how many input channels are there at each layer and how many output channels are there. So this is the important part. We have a memory hierarchy, which is very important, as we know that processors also have a memory hierarchy. Like registers are the fastest, then second fastest are cache, then the third fastest is the actual DDR memory, which is the slowest. So even we have a memory hierarchy. Our slowest memory is the RAM, which is DDR4 RAM. It is extremely slow, so we don't want to use DDR4 RAM except in the initial stages. Then we have something called URAM, which is on the chip itself. It is very fast. Then we have something called DRAM, which is also on the chip. It is also faster compared to DDR4. So we try to store most of our data in URAM and DRAM, because as you can see, the latency is extremely less. So URAM has 3 cycle latency only. DRAM has only 1 cycles. Whereas if we try to load from the RAM, we will have more than 100 cycles of latency. The trade-off is that DDR4 and URAM have much more bandwidth. So bandwidth is how much data it can supply at once. So that depends on the size of the bus carrying the memory. If you have a wider bus, you can supply more memory at one time. However, we are more concerned with the time, the latency. So we will be trying to fit most of our data in URAM and DRAM. So this is the structure of the URAM. You can imagine URAM as a 2D matrix. It has 8 banks, which are 8 rows, and 8 URAMs per bank. So you can imagine 8 URAMs as 8 columns. So we have 8 into 8 columns. Each column has 72 bits. Each column row, each element is 72 bits wide. Now let us talk about pipelining. So we must rely on something called the pipelining, because let us say we have read the URAM read, then we are processing convolution, and then we are going to write output. While we are doing this, the next pixel will be waiting till we finish the entire cycle. So this is not required. If the first pixel is in third stage, the second pixel can be in second stage, and the third pixel can be in first stage. So we don't have to wait for the first pixel to finish the entire process, then take the second pixel and start the next process, then take the third pixel and go to the next process. We can pipeline it, which means the first pixel to enter will, when it comes to second stage, then the next pixel can enter in the first stage. So in parallel, multiple pixels are being processed, just that they are in different stages in the pipeline. So like this, we have 2 pipelines, and we must make sure that the output of the pipelines are synchronized. So since the same pixel is going in both the pipelines, the output also should come out at the same time. Another advantage that we can use is something called int8 quantization. So most of the registers on a microprocessors are fixed in size, either 8 bits or 32 bits or 64 bits. So most of the registers are fixed, which means the native data type is also fixed. So that means you can the fastest would be 32 bits using, or the fastest native data type might be 64 bits. However, when we design our accelerator, we can decide our own register sizes, and more importantly, we can decide our data type. So we are using int8, which means 8 bits, 8 bits for representing numbers, only 8 bits. This is compared to FP32, which uses 32 bits for representing a number. Now the trade-off is that FP32 is more accurate because it has more bits, so it can store the decimal point much more accurately. Whereas since we are using an integer, or that also only of 8 bits integer, So we have less accuracy, but on the flip side, we get much more energy efficient because our size is less. Size per data is less. So we are using int8 quantization. So the benefit of the accelerator is that we can design our accelerator to be extremely fast with int8. So we can completely ignore other data types like floating point and a lot of the other data points such as dword, and there are multiple data types in a modern CPU. So this is again the same trade-off between generality and speed. A CPU has to support multiple data types, so it will take much more logic and much more transistors and much more area and much more power because it needs to support all the possible data types. Whereas our accelerator can be highly specialized and it can only target one data type, which can make it extremely power efficient and extremely performant. This is the comparison between the von Neumann architecture and static data flow architecture. So the von Neumann architecture is what is being used in microprocessors, all the microprocessors like 8085 or our Intel processors which we use in our laptops. All of them are based on the von Neumann architecture, which means there's a program counter which will tell the processor where to fetch the instruction from. The instruction will be fetched, decoded, executed, and then the result will be written back. So the memory instruction. So this is the von Neumann architecture. Whereas in our data flow, there is no instruction fetching and decoding. It is all just data that is flowing continuously through the pipeline. So like I described the pipeline before, the data is just continuously flowing on the pipeline. We only have two signals, which is valid and ready, which indicates whether the FPGA or the accelerator is ready for more data or not. As soon as the FPGA is ready for more data, data just starts flowing in, and so it's like assembling a car. So if you have seen an assembly line in any industry or any factory, the data keeps coming in or the materials keeps coming in and it keeps getting processed one by one. So there is no fetching the one data, operating on it and then storing it back. It's not like that. It is one by one the data will keep flowing in and it will keep being processed. So that is our data flow architecture. Now we will quickly just see the benefits of this in real time. So I have implemented this on the FPGA board. You can see that this is the resource utilization of the FPGA board. I will not go much into this, but more importantly is to see that we only are taking 4 to 5 watts of power on our accelerator. Whereas even if you take a normal laptop today, it runs mostly on 40 watt power or 45 watts power if you check your laptop adapters. So the power is at least 5 to 10 times of the power that we require. So this is our performance metric. We can see that we are only taking 61 milliseconds to process one frame, one image. We are taking only 61 milliseconds, and the image resolution is this 416 into 416 pixels. So comparatively, if we compare this to an ARM processor, so ARM processor is a very modern processor. It's a very optimized processor, as we all know. If we write a software which is very naive and very not optimized CNN network, the amount of time it will take to process one image is almost 30,000 milliseconds. If we try to write highly optimized software, like if an expert writes the software or something that you might see in OpenCV, if you have ever done image recognition in OpenCV, so those models are highly optimized, the software. If I try to run an optimized, even then I will require 640 milliseconds to run image detection on one CNN. FPS will only be 1 FPS per second, so only 1 frame per second. This is not usable in a real life scenario at all. Our custom accelerator can do 61 milliseconds of latency, almost 10 times faster, and the power efficiency is almost 5 to 10 times faster also. So this is the trade-off between general purpose CPUs and custom accelerators. General purpose CPUs, they lack the spatial parallelism. They do not have parallelism to this extent, and they do not also have the special hardware to deal with these very highly specialized operations. They need to be general and they need to target a lot of operations and a lot of data type, which is why they are very slow for such use cases. So just to conclude with everything, what did we trade away? We traded away generality. So that means we cannot have any, we cannot run any other algorithm. So we cannot run any random workloads on our accelerator. We can only run CNN model on our accelerator. So there will be no if-else statements. You cannot do like computations or any other algorithm other than CNN algorithms. We also can only use int8 data type, which means we are losing little bit accuracy compared to the CPU's FP32, but in return we are getting much better performance per watt. And also we cannot retarget our accelerator. So suppose we want to change our accelerator to something else, some other algorithm. Now we don't want to run CNN, we want to run suppose LLM. Now we have to change the architecture and the silicon of our entire accelerator. Whereas if on a CPU, we just have to change the software and recompile using any compiler. So it's a matter of minutes. Just change the CPU code, C++ code or Python code, and just run it on the CPU. Whereas if you want to change the algorithm, you have to change the silicon logic itself, and that will take a lot of hours of Verilog coding and then deploying on the FPGA. So that is again our trade-off. So the key takeaways are that we cannot just buy a faster CPU anymore. So the clock frequencies are not increasing from megahertz to gigahertz to further beyond. It has reached a saturation point. So this is why we need custom accelerators. So we have CPUs, which is the general purpose. It is the intelligent machine. But then we have these special accelerators in every chip now, which is a GPU used for graphics and AI, NPU again used for AI, DSP used exclusively for signal processing. So these are workloads that the CPU is not very fast and efficient as. So we are starting to create special chips for special processors for these type of workloads. But we still obviously need the CPU to do all the intelligent algorithms and all the controlling part. Accelerators, the reason accelerators win is because they remove the overhead. So like we discussed, most of the CPU's energy is spent in the fetching the instruction, decoding the instructions, controlling the pipeline, etc., etc. If we have a fixed data path, then we don't have to do all this fetching, decoding, and pipeline control. And we saw that we can easily get a 10.5x optimization over a already optimized CPU code. So the CPU code was highly optimized already. It was written by OpenCV professionals. So it was written by professional software engineers. So the point is that no matter how efficient software you are able to write, how efficient your code is, still because of the CPU's architecture and the CPU overhead, there is a ceiling on the performance that you can achieve. If you want to go beyond that performance, you will have to design your own chip. So this is why we are seeing many companies, AI companies are trying to design their own chips. Even GPUs are not power efficient anymore, actually. Because even GPUs take up a lot of power. So now the companies are trying to design their own specialized chips. You might have heard of Google's Tensor Processing Unit, TPU. So that's also a highly specialized optimized chip for AI inference. Now we will just look at a live camera demo of my custom accelerator running object detection. So as you can see, it is able to detect these objects. So this is a property of the model. I have not trained the model on my own. So the model has already been trained, and as I move the board around, you can see that my accelerator is able to detect objects rapidly. So this is the conclusion that we are able to achieve almost real-time object detection using just a board which consumes less than 10 watts of power. Compared to even a normal CPU, even a normal laptop might struggle to reach 30 FPS, even though it consumes 45 watts of power. So this makes it suitable to be deployed in systems like CCTV, traffic light stops, or industry. In factories, you can deploy object detection to classify whether the product is faulty or if it's proper. So these workloads require less power consumption, small area, etc., etc. So this is where these are the workloads where such a custom accelerator might be useful. Thank you.